All right, guys. Today, the goal is to solve equations that involve trig functions. And those trig functions for now will only be sine, cosine, tangent. So just to kind of, I said this in the email, just be careful, right? We're doing all this inverse trig stuff. When we solve equations, we're not going to think about the inverse function. So I just want you to kind of, put that to the side for now. Okay, so two things you need to remember before we get started. The sine wave and the cosine wave. Just a quick recap. When you graph sine, for example, it goes up, down, up. All right, and the initial period is 2 pi. And then you have a replication after 2 pi. So basically, for every solution you find, let's say you find a solution here, well, that means if you add 2 pi, you're going to have another solution here where the wave starts to replicate. So that's going to be important. It's going to be important to know that if you find a solution to a trig equation that involves sine or cosine, and then you add 2 pi to that solution, to that x value, you get another solution. And you add 2 pi again, you get another solution. So knowing that the period of sine and cosine is 2 pi is going to come into play in a big way. Okay, that's going to be a big part of how you write your solution set. Okay, so got that. That's not bad. Students generally don't have problems with sine and cosine. But where you have to be careful is that tangent has a period of pi, and that some of us got tricked by that on the test where you had 2x and you had to divide the period by b, and the period was pi over b and all that stuff. So just to remind you, the original, right, graph of the tangent function, right, we graphed one full period between negative pi over 2 and pi over 2, and the curve looked something like this. So if I find a solution for the tangent function, let's say the solution's here, then I'm not going to add 2 pi, right? So if I find one solution on the trig function, on the tangent function, then I'm going to have another one if I add pi. I'm going to have another solution here. And then if I add pi again, I'm going to have another solution. So that's going to come into play as well. For the tangent function, every time you find one solution, there are infinitely many solutions. So if that's a solution, I'm just making this up. Let's say one of your solutions is pi over 3. Then another solution is pi over 3 plus pi. And then pi over 3 plus 2 pi. Then pi over 3 plus 3 pi, etc. So that's going to come into play, and we'll talk more about that as we go. But it is important to know the period. All right, let's dive into our first example. So with trig functions, you're going to have one of two sets of directions. You have what I call the easy set. All right, so the easy set of directions is solve this equation for theta and only find all the solutions between 0 and 2 pi. Now, if 0 is a solution, then you just say 0 is a solution, not 2 pi. We know that 0 is an angle and 2 pi is an angle are virtually the same angle. They're coterminal. So that's the easy thing. Just go to the unit circle, find all the solutions between 0 and 2 pi. The other set of directions you'll see as we work multiple sets of, CUDA worksheets and Word documents and quizzes and tests and all that, is to write the general rule. So I'm going to show you both, the easy and the general rule, which is a little strange, and I'll explain why you're writing the general rule one time, and then we'll just work problems. Okay, so the first example is going to take a little while because I really need you to understand what you're doing, and then once you understand what you're doing, you can just go through the process and just crank out some problems. All right, so here's what we got. Cosine of theta equals 1/2. You go to the unit circle. So the question is, and we're not thinking inverses, we're not solving equations in the traditional way of undoing cosine, okay, because that'll kind of lead us astray. So the question is, what angle will give me out 1/2 where it's cosine, right? So that means that's my x-coordinate on the unit circle. So if I go to where the x-coordinate is 1/2, I'm here, I'm at pi over 3. And then there's the second angle. There's another x-coordinate of 1/2. So that's down here. So that's at 5 pi over 3. So for a basic equation, that's all that's happening. There are two solutions. So if the directions say solve each equation on the interval where theta is from 0 to 2 pi, the first solution, so theta is pi over 3, or theta is 5 pi over 3. Those are all of the solutions that live between 0 and 2 pi. Easy peasy, right? Now, if we're thinking about the cosine function writ large, right? So if you're thinking of the entire cosine function that goes on forever and ever and ever and ever and ever and ever and ever, here's what we just found. We just found when the height of the function is 1/2, we have a solution here and here. We just found pi over 3 and 5 pi over 3. Now, is that every single possible solution for theta? Of course not, because this curve goes on forever. We just found one of them. Where's the other one at the replication, right? So you need to take pi over 3 and add 2 pi to find the next one. And then add 2 pi again to find the next one. What about 5 pi over 3? So 5 pi over 3 lived here. Is that the only one? No. If you add 2 pi to that, you get another one, and another one, and so on and so on. So the general rule is written like this. For every angle that you find for cosine and sine, let me say that again. For every angle that you find between 0 and 2 pi for sine and cosine, the general rule is this. Pi over 3 plus 2 pi k, where k is an integer. There's only one R in the word integer. One of the most misspelled words in algebra nomenclature. Integer. No, integer. Okay, so pi over 3 plus 2 pi times 1 plus 2 pi times 2. And you can go to the left. So it could be 2 pi times -1, which means -2 pi, which means you're moving left 2 pi. Okay, so the general rule for sine and cosine is find the solution and then tack on plus 2 pi k, meaning infinitely many solutions, all of a certain form. And then the other is the other angle between 0 and 2 pi. So for each angle on the unit circle, if you're writing the general rule, you have to take 5 pi over 3 in this case, and add 2 pi k again. Okay, so two sets of directions, just to be clear. If you're only solving for the angles that live between 0 and 2 pi, meaning you're only asked to find a certain range of solutions, then easy peasy, go to your unit circle, find your solutions. Sometimes there's only one, sometimes there are two. You'll see problems next week where there might be 4 or 8. Those can get kind of messy, just finding some of the solutions on the unit circle between 0 and 2 pi. But if you're asked to write the general rule, the answer is going to look like this. Meaning you're saying these are all of my solutions, not just 2. This literally represents every single solution to the original equation. All right. So that's the meat of the lesson. Now let's just do some examples. So the rest of the lesson is just going to be us cranking through some examples together, and we'll stop to talk about tangent a little bit like we did here with cosine, because sine and cosine you want to think about differently than tangent. All right, so now tangent. So think of example 1, cosine. It could have been sine. Virtually the same problem. Now we have a tangent equation, a little bit different. So tangent, remember tangent, you really have to think backwards. So the question is, for tangent theta, what angle is going to give me out -√3, negative square root of 3? So let's kind of look backwards on that one. Where did √3 come from? though you're getting tired of hearing me say this, but that came from this. Or, right? So remember, we're not thinking tangent inverse anymore. We're just thinking any angle that's going to give me negative root 3 has to come from this y value and this x value when you simplify, or this. Okay, so one of these pairs of coordinates, y over x, where one's negative or the other's negative, is going to give me out negative root 3. Okay, so let's go to the unit circle and let's find those coordinates. So the question is, which angle gives me a y coordinate of negative root 3 over 2? So a y coordinate of negative root 3 over 2 is down, but I have a positive x coordinate. So down negative root 3 over 2 and over 1/2 takes me here. Okay, and I'm taking my time with this because I really want you guys to see that tangent's nice, but it can be tricky at the same time. And the other one, so positive root 3 over 2, but negative 1/2 takes me here. So let's call this one. So here I have positive 1/2 as an x value and negative root 3 over 2. So here's one of my solutions. I know this angle is 2 pi over 3. And I know the other angle, the green angle. So let's make green here. That green angle is 5 pi over 3. So here's where tangent gets a little weird. If you're just asked, find all the angles between 0 and 2 pi, in this particular case, there will be two solutions. So when will tangent of theta be negative root 3? Well, when theta is 2 pi over 3. Or when tangent is 5 pi over 3. Those are my two solutions. But if you're going to write the general rule, here's where it gets a little weird, and it's not really that bad. But so the period of tangent is pi. So if you're going to generalize this, let me show you a graph. Okay, and I'll do this just one time for the sake of clarity. Here's the original tangent function. Okay, pi over 2. Then we draw another graph at 3 pi over 2, another asymptote. So remember, the original period was pi, so every time I add pi, I get a new asymptote, So that's 3 pi over 2, 5 pi over 2. And you can do this in Desmos. You can just graph tangent of x, and you'll see all of these waves that I'm graphing right now. Just replications of that same graph. And then here's what I want you to see. When you write the general rule, so this is only true for the general rule. If you're asked to solve each equation on the interval from 0 to 2 pi, well, you just go to the unit circle and you find, in this case, two different answers. That's the easy problem. Once again, let me just call it that again. That's easy. We've been doing that forever. Find the angles on the unit circle. But when you generalize, you've got to be careful because you will lose points for redundancy. Here's what I mean by that. If you go to Desmos, which I didn't go to Desmos, but we have one portion of the graph from negative pi over 2 to pi over 2. That was from negative pi over 2 to pi over 2 on the unit circle. That is where we built the inverse function, but we're not there. So the question is, where is 2 pi over 3? 2 pi over 3 is about right here, which means that's where my solution came from. The question is, what angle gives me out a y value of negative root 3, and that's it right there, 2 pi over 3. That's my x value. Okay. Now, if I add pi to that, boop, it takes me here. If I take 2 pi over 3 and I add pi, I get 5 pi over 3. And if I add pi again, I get 8 pi over 3. You see the pattern? 2 pi over 3, 5 pi over 3, 8 pi over 3, 11 pi over 3. I can find solutions all day long, but when I say redundance, here's what I mean. If you're asked to write the general rule for tangent, if you take 2 pi over 3 and you add pi, it takes you here, 5 pi over 3. And if you add pi again, and add pi again, and add pi again. So the general rule for this problem is simply 2 pi over 3 plus pi times k. That is the general rule. Okay? So I just want to be clear. If you're asked to find solutions between 0 and 2 pi for tangent, you're going to get two answers, but the general rule will capture both of those. So there's only one general rule. And if you want to test this out, you can test this out. If you take, remember, k can be any whole number. So if you take 2 pi over 3 plus pi times 1, you get 5 pi over 3. 2 pi over 3 plus pi times 2, you get 8 pi over 3, and so on. So the general rule for tangent can be a little tricky, but it's only because you're thinking in terms of 2 pi, but tangent has redundance. So basically, every time you have one solution on the unit circle and you go exactly pi halfway around the circle, you will always have a second solution when you're doing the easy problem. When you're writing the general rule, you don't need to write 2 pi over 3 plus pi k and then 5 pi over 3 plus pi k, because that's redundant. All right, this general rule includes the 5 pi over 3. Okay, so that can be a weird point to understand. So of course, if you have questions about that, you can shoot me an email and we'll talk about it. All right, so now we've done all the theory and all the little sketches and all the conversation and all the details. Now we're just going to blast through examples 3, 4, and 5, which are straight solving equations in the true sense. All right, so let's look at example 3. So example 3 is just solving the equation. So think of sine theta as like the variable. I need to get the variable by itself. So this is going way back to 6th or 7th grade when you first started solving equations. So think of this as 2x plus something equals 0. If I want to get sine theta by itself, I subtract root 3 on both sides. That leaves me 2 sine of theta equals negative root 3. You can kind of see where we're going. And then 2 times sine of theta, I need to divide both sides by 2. Sine of theta equals negative root 3 over 2. Boom! Now we're back to just basic, what's the unit circle, right? So what angles, once I get sine theta by itself, what angles give me out negative root 3 over 2 on the unit circle? And I'll write the solutions as all angles between 0 and 2 pi, and I'll also write the general rule. Okay, so what are the angles? Let's start with that. Let's find the answer. That give me out a y value of negative root 3 over 2. So one of my angles is going to be 4 pi over 3. That takes me down to negative root 3 over 2. And the other one, 5 pi over 3. 5 pi over 3. So my two answers are 4 pi over 3 and 5 pi over 3. Now for general rule, I would write my solutions, meaning all of my solutions. Good Lord. 4 pi over 3 plus 2 pi k, 5 pi over 3 plus 2 pi k, if I'm asked for the general rule just to differentiate. So the easy, got it, general rule for sine and cosine, just tack on the add 2 pi because there are infinitely many coterminal answers that give me the same y value when I go around the unit circle. All right, on to the next. Boop. Let's work at a secant theta problem. So once again, get secant theta by itself. Okay, so the first step, subtract 6 on both sides. 4 secant of theta equals -8. Divide both sides by 4. -8 divided by 4 is -2. Now here's the beauty of secant. We always think of it in terms of cosine. So if we're trying to solve the equation secant of theta equals -2, that equation is 100% equivalent to, meaning has the same solution set as, cosine theta of the reciprocal. We've played this game over and over, right? So the reciprocal of -2 is -1/2. These two equations, just to be clear, are equivalent. They absolutely have the exact same solutions. So every secant theta equation can be, once you get secant theta by itself, can be converted to a cosine problem of, right, where the output is the reciprocal. So as soon as you see secant, think, get secant by itself, secant of theta, and then convert it to its equivalent form in terms of cosine, and then it's an easy problem. So, unit circle. I want to know where is the x-coordinate -1/2 for which angles. So an x-coordinate of -1/2 takes me to 2 pi over 3 and to 4 pi over 3. So theta is going to be 2 pi over 3 or 4 pi over 3. The general rule is going to be theta can equal 2 pi over 3 plus 2 pi k, or 4 pi over 3 plus 2 pi k. So once again, all of the handouts are going to have one set of directions. You don't always have to do both. Now, if you just want to do both to get in the habit, that's fantastic, but you don't have to. Just pay attention to the directions. What's important is if you're asked for the general rule and you don't write what I have in the yellow box, that's a problem. Now, if you're asked to find only the solutions between 0 and 2 pi and you give me more, you give me the general rule, that's even better. But if you only write what I'm highlighting green when you're supposed to give the general rule, then that's where you have to be careful, because the general rule is literally every single solution where, given this interval, you've just found two particulars. All right, last example. Bow. All right, last but not least, there's a little bit of notation here, so let me talk about that for a second. Trig always presents kind of new notation, so let me write this real quick. So you have this notation of sine squared of theta. That looks strange, it is wonky. That actually means, just to be clear, that means you're going to find sine of theta and square it. So it's a kind of a shorthand or a different way of writing something squared. So I know it looks like you're squaring sine, which doesn't even make sense, but it literally means sine theta squared. And the reason that is, so here's what you're looking at. If you want to take the value of a function and square it, you would write it like this. Okay? So with sine, you're actually writing it kind of like this, which is weird. You'll never see that notation with regular functions like f of x, g of x, t of x, c of x in a science class or a physics class. So this looks crazy. It doesn't even make sense. So you'll never see that. Only with trig functions will you see sine squared of theta, which literally means sine of theta squared. Okay? So this equation, just to kind of talk a little bit more about it so we're clear, is basically like a quadratic equation. So it's similar to 2x squared minus 1 equals 0. If you were going to solve this equation, so let's look at this, you would get x squared by itself, and then you would take the square root of both sides to solve for x. We're going to do the same thing when we see sine squared of theta, tangent squared of theta, cosine squared of theta. Okay, so let's solve this. Let's get sine squared of theta by itself, just like we would any other equation. So I'm going to add 1 to both sides. That takes me to sine squared of theta equals 1. I'm going to divide by 2, and I'm left with, okay, equals 1/2. Now, once you get there, you take the square root of both sides. So that's just like if we were to have x squared equals 9, like we did with the Pythagorean theorem. You would take the square root of both sides. Okay, now, I just want to remind you, there are two numbers that make this equation true. 3 squared is 9, and negative 3 squared. Negative 3 times negative 3 is also 9. So when you take the square root of both sides, don't forget plus, minus. Always two solutions. So when we take the square root of both sides, all right, the square root of the left side is just sine of theta, all right? But when you take the square root of the right side, you get the square root of 1/2. Don't forget the plus or minus. Okay, now it's been a minute, so let me just remind you, the square root of 1/2, so let me simplify this off to the side. The square root of 1/2 is the square root of 1 over the square root of 2. So there's that property. Once again, we've seen this a couple times, where if you have the square root of a ratio, the square root of a quotient, it equals the quotient of the individual square roots. There's a property that allows you to do that, which gives me the square root of 1, which is 1, the square root of 2, and then I rationalize the denominator, and that gives me root 2 over 2. So you might have forgotten this, but you've seen this, and this is way back when we started unit circle stuff. The square root of 1/2, that is root 2 over 2. The root 2 over 2 came from taking the square root of 1/2. So just to kind of remind you, you don't have to know that, but it's nice to know that every time you take the square root of 1/2, you can just instantly write sine, in this case sine of theta, plus or minus root 2 over 2. Okay, so here's what we've done. We've done what we've done in number 3 and number 4. We have now got sine theta by itself. Okay, so I'm going to go to another screen because this one's been all kind of marked up. But if you see sine squared, tangent squared, cosine squared of theta, you would solve for the trig function of theta just like you would any other equation. Okay, so that takes us to a new problem. So we had to get sine theta by itself first. Now we're here. Sine of theta equals plus or minus root 2 over 2. So this one's interesting in that you don't have to write what I'm writing right now, but this is helpful. This means that sine of theta can equal positive root 2 over 2, or sine of theta can equal negative root 2 over 2. So they're really like two different sets of solutions. So let's go to the unit circle and play that game we always play. What angle gives me out root 2 over 2? Pi over 4 and 3 pi over 4. So theta could be, pi over 4 or 3 pi over 4. Okay, if my y value is root 2 over 2. Or if it's negative root 2 over 2, my y value, then I could be at, so theta could be 5 pi over 4, brain stopped working for a minute, or 7 pi over 4. So this particular solution, this particular equation, on the interval from 0 to 2 pi, like one full rotation around the unit circle, actually has 4 different solutions. So if you're going to write a general rule for this, if you take any one of these angles, which none of which are coterminal, and add 2 pi, you get a new solution. So for the general rule, there are actually going to be 4 different general rules. You have pi over 4 plus 2 pi, 4 pi, 6 pi, etc. So remember, we write plus 2 pi k. We also have 3 pi over 4. And I'm just going to write 2 because I'm lazy. So if we start here and add 2 pi, we get infinitely many solutions. And then we have 5 pi over 4 plus 2 pi k and 7 pi over 4 plus 2 pi k. So just to be clear, if you're asked for the general form, then this is how you would write it. Ooh. So you would write it like, all right, PowerPoint, work with me. So if the general rule, this is what I would write, okay? And remember, the quotations just mean same, 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 okay? So you have solve in a given interval, 4 solutions in this particular case, or 4 general rules, and that's it. All right, guys, so my hope is you now can solve a trig equation. You can find sine of theta, cosine of theta, tangent of theta, given some output using the unit circle. And just to remind you, we did not use inverse functions at all here because the inverse function would only give us one solution, where in general there are infinitely many solutions. So we're thinking about solving equations differently than we have in the past. All right, guys. So hopefully you took good notes. You remember that sine and cosine live, you have solutions basically every 2 pi k. Tangent, you have solutions every pi k. Practice, check your solutions, and send me emails as soon as you have issues, and I will see you guys in class.